Okay, everyone. So we're moving into chapter 2, and we're going to be talking about reasoning. We use a lot of reasoning, like what we used in assessing the validity of definitions in class today. And we'll also use reasoning when we're constructing proofs. So first things first, we got to figure out what we mean when we're talking about reasoning. Excuse me. And geometry, of course, is pretty particular about how we describe that. So let's start by talking about conjecture and inductive reasoning. You probably saw this in Algebra 1, though you may not remember it. Conjecture is an educated guess based on inductive reasoning. And inductive reasoning is just reasoning that's based on patterns you observe. So we're going to observe some patterns, and we're going to make some conjectures in a second. Here, I'm going to let you read this little cartoon here first. And for the record, oh my goodness, just so you know, Winston Churchill is who's referenced in this cartoon, and he was a great orator and a great writer, but apparently didn't do very well in English. And that was true for Einstein too. His science and math were his field, but he at one point actually flunked math. Okay, so let's talk about patterns. Let's say we have the pattern 1, -2, 4, -8, 16. What do we notice about that pattern? How do we get from 1 to -2, from -2 to 4, from 4 to -8? And once we've figured that out, we can probably guess what the next two, or make a conjecture about what the next two terms would be. So first, let's notice that we could either add -3 to 1 or multiply 1 by -2 to get the next term. Well, if we added -3 to -2, we would end up with, right? And that's not this term. But if we multiply by -2, we do get a +4. And then, oh yeah, look at this. Multiply by -2 and multiply by -2. So what are my next two terms? Well, what's 16 times -2? That would be -32. What is -32 times -2? That's going to give us 64. So we made a conjecture that these are our next two terms in this series. It's a pretty educated guess, though, based on all of the numbers that come before it and the pattern that we observe, right? What about if we did the same kind of thing with geometric patterns? Excuse me. So this is, if we were to say, let's call this purple, green, red, purple, green, red, purple. What are the next two figures in this sequence? Color and shape. So we have two patterns that we have to discern or observe in this particular case. But it's not that hard, right? It's not that different than things we've done in the past. I'm going to first do the color and say, okay, well, see, purple, green, red, purple, green, red, purple, green, red, right? So I'm going to have green something and red something. I haven't figured out what the shapes are yet. I have triangle, circle, square, triangle, circle, square, triangle, circle, square. So my next two shapes are going to be a green circle and a red square. Not rocket science, right? So that's all there really is to inductive reasoning. It's just about noticing patterns, and we draw conclusions or conjectures based on those patterns. Sometimes, though, we have to, just like with our definitions in class today, we have to actually assess the validity of our conjectures. or our arguments, or as in class today, the validity of our definitions. And so one way to do that is to see if you can come up with a counterexample. So Eric is driving his friends to school when his car suddenly stops, and he makes the conjecture that his car battery died. Well, is that the only possible explanation? No, right? He could have run out of gas, or a whole lot of things that could have happened. So is the conjecture valid? It is not. It is not valid because it's not the only possible explanation. And in geometry, when we're talking about conjecture, it needs to be, when we make a statement in geometry, it needs to be true all the time, or as far as geometry is concerned, it's not true. So let's try an example. I want you guys to try this, to stop the video and try this on your own. If you're given points P, Q, and R are collinear, and we know what that means now, right? If we're given that those are collinear, I'm going to say that Q must be between P and R. That's my conjecture. P, Q, and R are collinear. Q is between P and R. Is the conjecture valid? Can we think of an example that disproves the conjecture? Or can we think of a counterexample? And hopefully you're actually taking the time to try and work that out in your notes. But, well, here's what I think. I can think of an example where P, Q, and R are collinear, but Q isn't between P and R, right? Because Q, P, R, they can be collinear in this order. They don't have to be in the order they're listed. We can put them anywhere we want because we're not given any more information in the problem. All we're told is that P, Q, and R are collinear. They could be collinear this way. They could be R, P, Q, right? Lots of different possibilities. So we thought of a counterexample, which means that this is not a valid conjecture. I want you to try this one in your notebooks, and I'll be checking your notebooks tomorrow. I just want you to try this on your own. I want you to find a counterexample for each conjecture. And we will be doing this a lot in the next few weeks. We'll be talking about conditional statements and conjectures and contrapositive and a lot of this type of reasoning. So take the time to really think it through. If a flower is red, then it is a rose. Is that valid? Can you think of a counterexample? One and only one plane exists through any 3 points. Is that valid? Or can you think of a counterexample? And when you multiply a number 3, then the product is divisible by 6. Is that valid? Or can you think of a counterexample? Okay, that's it for today. I will be checking your notebooks tomorrow. Have a good night, everyone.